In the next few videos, we're going to look at the divide and conquer design paradigm. So again, this is a generic, fundamental design technique, one that we can use and apply it to a variety of different problems. And in fact, you've already seen this before with merge sort. Merge sort is a kind of divide and conquer algorithm. So we're going to look at merge sort again, and in particular, we're going to look at how we can express the running time of a divide and conquer algorithm. Because it's a recursive type of algorithm, we can express the runtime using a recurrence equation, but then in order to put that in big O notation, we've got a few different ways where we can put it in closed form so that we can evaluate the runtime asymptotically, so we can put it in big O notation. So we'll see a few different ways that we can do that, and then see another example of a divide and conquer algorithm lastly. So what is a divide and conquer algorithm? Just to kind of refresh your memory here. So we've got 3 steps: divide, recur, and conquer. Our first step is to divide whatever our original input is into smaller sized disjoint inputs, meaning two smaller sized inputs don't share any of the same values. Or maybe we have 3 or 4, just 2 or more smaller sized disjoint subsets of our original input. So if we look at the execution tree, this is what it may look like. So given our original input, we break it up into smaller sized subproblems where each subproblem does not overlap. And then we recursively solve for those smaller sized subproblems. And usually the base case for our recursion is when we have subproblems of constant size, where this is easy enough to solve directly on them. So for example, for merge sort, when we were left with just one item, this is already sorted, we don't have to do anything, and we are finished. So our base case is when we have subproblems of constant size, maybe 0 or 1 or 2 elements left. And then in the conquer phase, we take our solutions for these subproblems and use them in order to give us a solution for our original problem. Now, because this is a recursive kind of algorithm, we can express the running time of our divide and conquer algorithm using recurrence equations. So let's look at merge sort again. So we've got, remember this was that we are given some sequence S, and we have a comparator, so a way to compare elements since this is a comparison-based sort. And we take our original sequence, let's draw it here. We take our original sequence and we just partition it exactly in half if we've got enough items in here. So this is just the first half and the second half, S1 and S2. And then we recursively call merge sort again on S1 and on S2. Now that we have 2 already sorted lists, S1 and S2, our last step is to merge these now sorted lists into one sorted list. So if you remember, this was, let's say here's S1 and here's S2. Our generic merge algorithm, this worked by kind of combining these to form a sorted list consisting of all of the elements from S1 and S2 by starting at the beginning of S1 and the beginning of S2, comparing each element and taking whichever one is smallest, removing that one, and then adding it to our now sorted list, and then taking the next element from each one. So the first item in each list we compare against, and then we take whichever one is smallest. So one by one we go through every item in S1 and S2, and we add them to a sorted list S, which consists of all of the items from S1 and S2. And this was our merge sort algorithm. Our base case for recursion was we're assuming that we have a large enough size input, because if we just have 0 or 1 elements, then that list by itself is already sorted. We don't have to do anything. Now, we can express the runtime of merge sort using a recurrence equation. So the idea is the runtime of merge sort, T of n, this is the runtime of our merge sort algorithm, is we can break it up into 2 steps here. So if we have a small enough input n, so this was our base case, then the total running time was constant. So B just represents some constant number. So if we have less than 2 items, and we call merge sort on less than 2 items, we don't have to do anything. We have 0 or 1 item, we just check to see the size, and then we return that list, because just 0 or 1 element by itself is already sorted. We don't have to do anything else. So if we have a small enough size input, the running time, t of n, is constant. But if we have a large enough input, then we divide our problem into subproblems, we recursively call on those subproblems, and then we conquer. We take the solutions to those subproblems, put them together, and turn them into a solution for our original problem. So we have how many subproblems? We had 2 subproblems. We broke it up into the first half and the second half. And then each of our subproblems was of size n over 2. So this is the size of our subproblems, n over 2. And then we had some linear amount of non-recursive overhead. So this was for merge sort. This was coming from the conquer step where we merge 2 already sorted lists into 1 sorted list. So the running time of merge sort, if we have a large enough input, is equal to whatever it costs to call merge sort again. So here, this is the runtime of merge sort, t of n over 2, if we call merge sort on an input of size n over 2, and we do that twice. So this is the recursive overhead that we incur, plus the non-recursive overhead that we incur, which is coming from the divide step and the conquer step combined. And for merge sort, this is linear. This comes from, we have some constant number times n, and this comes from merging 2 already sorted lists and putting it into 1 list. So we've got, this is our recurrence equation. So this is describing the runtime of t of n in terms of t of smaller sized n. So if we want to put this in big O notation, we want to say that t of n is n log n. We at least know that from when we talked about merge sort. But that's not immediately clear from our recurrence equation. So we want to figure out a way that, given a recurrence equation, how we can put this in closed form, meaning we have t of n only on one side. So we want to say, for example, that t of n is equal to some function which doesn't include t of n, some function of n. That way we can say, oh, if this is the case, or even if t of n is less than f of n, less than or equal to f of n, then we can solve, put this in big O notation and say that t of n is big O of f of n. So this is what we want to do. So any divide and conquer algorithm, because it's recursive, we can express its running time using this recurrence equation. Now we want a way to, given a recurrence equation which represents the runtime of a divide and conquer algorithm, put it in closed form. That way we can express the runtime in big O notation. Something a little bit cleaner and simpler. So there are a few ways that we can accomplish this. One way, and this is how we had argued about merge sort last time, is by using a recursion tree to just kind of visualize what the runtime would be. So we have here, this is just the execution tree. So each node represents one call to merge sort. So we've got, this was our original input that we called merge sort on, and then we broke our input up into 2 smaller size sequences. Each sequence was half the size of our original input. And then we have base case when we have a small enough size input of just 1 or 0 elements. So how do we figure out the runtime using this recursion tree, using this execution tree? Well, we can figure out, in this case at least, since we know we'll have an even tree, we can figure out the height of this tree, h, and then figure out how much time we spend at each level of this tree. And our total running time will be how many levels we have times the cost of the non-recursive overhead at each level. So we saw from before that the number of times that we'll have to call merge sort, so if we're starting with n elements, the number of recursive calls that we'll have to make just going down kind of one line of this recursion tree is log n, log base 2 of n. So we have that the height of our tree, h, let's put it over here, the height of our tree is log n, which means we have log n plus 1 levels. So again, this log n is coming from, we start with n elements. This is exactly how many times we have to repeatedly divide by 2, divide by 2, divide by 2, until we're left with just one item left. And this is the base case of our recursive calls, since one item by itself is already sorted. So the height of this tree is log n. So this is the number of edges that we've got, which means that the number of levels we have is log n plus 1. And we're going to multiply this by how much time we spend at each level. So this is the non-recursive overhead now. So the non-recursive overhead in this case is coming from when we're merging two already sorted lists together into one sorted list containing both elements from both lists. So in this case, we've got n over 2 elements here and n over 2 elements here. We have a total of n elements that we have to combine into one, so the amount of time we spend here is just some constant number times n. If we look at the next level, so we want to count up how much time we spend merging these two smaller size lists of size n over 4 into this list of size n over 2, and include everything along that level. So also how much it costs to merge these two smaller lists, each of size n over 4, into one list of size n over 2. And this is based on the size of each of those lists. So this one runs in some constant times n over 2, and this one runs in some constant times n over 2, and we've got two of them, so the total cost for everything along this level is some constant times n. And the same holds for each one of these levels. So in this case we have 4 lists, but the cost to merge our two smaller lists into one for each of these 4 lists is the size of that list, which is n over 4, and we've got 4 of them. So our total cost, the amount of non-recursive overhead we're incurring across this entire level, is some constant times n. So this is b times n. So the cost incurred here, the total running time of merge sort, is however many levels we have times the amount of non-recursive overhead we've incurred from each of those levels. So this is how we get bn plus bn log n. You'll see in the next video how we could also solve this without using a recursion tree, using instead an induction technique.